Good evening, ladies and gentlemen, and welcome to Astronomy on Tap Atlanta. Thank you all for coming out in such numbers, in such heat. Welcome. Thank you so much. I am very excited. One, because we have never approached this topic in the almost 3-year history of Astronomy on Tap Atlanta, but it is my pleasure to also introduce Georgia Tech Physics PhD candidate, Urja Shah. Urja has been conducting gravitational wave research by using data collected from gravitational wave observatories such as LIGO, the Laser Interferometric Gravitational Wave Observatory, and she is just about a year out from defending her PhD. So everybody, please give one more warm round of applause for Urja!
Thank you so much, Justin, and everyone for the kind introduction. Like Justin mentioned, my name is Urja, and I'm a grad student at Georgia Tech, and I conduct research in gravitational wave astronomy. So today I'm going to talk a little bit about what that means exactly, and we will start off by going into a history of gravity itself. So the earliest records that we can find of gravity is from Aristotle in the 4th century BCE, who said that things fall according to their natural place. So heavier objects would fall towards the center of the universe, which was believed to be the Earth at the time. From there, we have an Indian astronomer, Bhaskaracharya, in the 12th century, who said that Earth has an unique and special attractive force, which is why things fall down towards the Earth. And honestly, he was much ahead of his time, because the next theory that we have is from the 16th, 17th century of Galileo, who said that all objects fall at the same rate, irrespective of their mass. Lastly, from there, building up on all of these ideas and culminating into one theory, we have Sir Isaac Newton in the 17th century, who came up with the law of unified gravitation or universal gravitation. So from here, Einstein came up, and we were really happy with this theory of relativity. For 250 years, we were happy. Then Einstein came along and said, "Hold my beer." So in 1915, Einstein formulated what we now know as general relativity, which states that gravity is not a force. It is the bending of space and time caused by mass and energy. Interesting, very cool concept that's taken a long time for us to understand what that really means. He also predicted two wild things as a part of this. One was black holes. The other is gravitational waves, and we will talk about both of these. Okay, so when we talk about what it means for gravitational waves to be, for gravity to be the curvature of space-time, we often see an image that looks like this. So heavier masses bend space-time a little bit more than lighter masses, and lighter masses sort of curve towards and around the higher mass objects. Jay Wheeler, a physicist, summarized this really well, and he said, mass tells space-time how to curve, and space-time tells mass how to move. So now talking about one of those other really wild postulates from Einstein, we have black holes and neutron stars. So when we look at a star and the end of its life, if a star has a low or a medium mass, it will collapse into a white dwarf. But if you have a really massive star, that explodes or goes out in a supernova. And depending on how small the mass is left over at the end of the supernova explosion, you either form a neutron star or a black hole. So a high mass star will give you a neutron star, and a very high mass star will give you a black hole. Now, we can think about what happens when two such objects collide. So two neutron stars, two black holes, one of each. That, as you can imagine, is a very energetic, very violent event. In this video here, that was actually made by Georgia Tech a couple of years ago, we see two black holes that are closely orbiting each other and releasing some energy as gravitational waves that you see, the ripples in the space-time fabric. Eventually, they merge into this unified singular black hole and radiate further energy away. So that is what we know as gravitational waves. Now, gravity waves is, people often call gravitational waves gravity waves. They are two completely different things. Gravity waves is a meteorology concept. They might be pretty upset if you call gravitational waves gravity waves. So what does propagation of gravitational waves actually look like for the space-time fabric, and what and how is that different? So if you imagine this ring of particles in floating around in space, and a gravitational wave is passing through it, you see that they stretch and squeeze in perpendicular directions, and they repeat that process as the wave is passing through them. So this is how gravitational waves propagate. It's the stretching and squeezing motion of particles. Now you may beg to ask that, okay, well, how far will they propagate until? The answer is indefinitely, towards anything and everything and the end of all of it. So this is an extremely dramatized, exaggerated video of what happens to Earth if a gravitational wave passes through it. As you can see, the Earth is also stretching and squeezing, which fundamentally is what happens, but this is extremely, extremely dramatized. In reality, this happens at such a small scale that we cannot even feel it. In fact, all of you, all of us, have gravitational waves passing through us all the time, and we don't even know it. Our bodies are being stretched and squeezed continuously. So what can make gravitational waves? If they're everywhere, if they do everything, if they're so unique? Well, the answer is also right about everything makes gravitational waves. As long as it has mass and it moves through space-time, it can make gravitational waves. So what can make loud gravitational waves that is potentially detectable by us? I have 4 such examples for you here. We have spinning neutron stars, colliding stars, that I mentioned before, such as neutron stars and black holes. We have events that we call bursts, which are short duration, transient events that could happen from things like supernova or some completely unknown phenomena. And lastly, even the Big Bang. So something that I found myself asking when I was a young undergraduate in this field is, what's the big deal? Why gravitational waves? Why not just light like we've been doing for centuries? And as I did more work, I found out that there's 3 main reasons. One is that we have been given a new way to see and understand the universe, see in quotations, because it's not light, we don't really see it, which provides us with a whole depth of information. The second that I find really important is that they travel unscathed. So they're not disrupted by gas, galaxies, dust, or anything else the way light is disrupted. It can just travel unscathed. And because of this too, we can have ancient relics to the Big Bang. Now, detecting these weren't as easy as I made it seem. Soon after Einstein's theory of relativity, attempts to detect gravitational waves started being made. One of the most famous ones was in the 1960s when Weber developed the first resonant bar detectors, which are essentially a system of large metal rods that will detect vibrations in them as a result of gravitational waves. He also claimed detections, but unfortunately, no one else was able to reproduce them. So we are not very confident about this method. So soon after, Rainer Weiss in the 70s formulated a laser interferometer method. And he got a lot of support for this and formed a joint collaboration between MIT and Caltech that we now know as the LIGO collaboration. And construction for this began in the 90s, and it was already observing in the early 2000s. Now, unfortunately, it still took us a really long time from that first creation and the first detectors to get them sensitive enough to be able to observe anything. So from here enters LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory, which is a form of the Michelson interferometer, if you're familiar with that. So this system has two long, perpendicular, 4 kilometers long arms where a laser beam is split into halves, and it is finally recombined at that mirror that you see at the end. If a gravitational wave passes by, there is going to be the stretching and squeezing that I mentioned before of those arms. And so when the recombination of these waves happen at that mirror, there's going to be a very small difference in those two waves that we can detect. Other fascinating or other important structural things in our system, we have 4 mirrors. We have one high power laser and an ultra high, in fact, arguably the most sophisticated vacuum system currently on Earth. Because even a small air molecule will disrupt our entire analysis. And LIGO is not alone. So LIGO is joined by numerous other gravitational wave ground-based observatories worldwide. To actually speak initially about LIGO a little bit, so LIGO forms these 2 joint detectors, one in Livingston, Louisiana, and another in Hanford, Washington. These were the first that we've had. Along with this, we also have GEO 600 in Germany that was unfortunately recently decommissioned. We have Virgo in Italy, the Kagra detector in Japan, and we have a LIGO India detector that is currently being built. So our network of detectors comprises of all of these around the world. You may also be asking, well, how many physicists does it take to detect gravitational waves? Apparently a lot. We have over 1,600 members, physicists, engineers, software engineers, data scientists currently in the LIGO collaboration. We span across 14 countries and 140 institutions worldwide. Also one of the largest scientific collaborations in the world. And here's Georgia Tech. Okay, I have a quick audience interaction moment. So we spoke about how small gravitational waves are. I have a fun question for you guys. How small do you think are the effects of gravitational wave on our LIGO detectors? And for reference, the width of a human hair is 10 to the negative 4 meters. And hydrogen atom, the diameter of a hydrogen atom is 10 to the negative 10 meters. Okay, so if you think the answer is A, 10 to the negative 12 meters, raise your hands. Okay, 1. Okay, 10 to the negative 15 meters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, not bad. What about 10 to the negative 18 meters? Okay, sweet. Yep, everyone else, you're correct. It is 10 to the negative 18 meters. And to give you that context, that is about 1,000 times smaller than a proton. That's insane. So now you may also be thinking, well, you guys sound like, I'm forgetting the word now. Oh my gosh. Like you're dreaming, essentially, because something that small, how can you detect it when literally everything else is much more noisier and louder? And that is true. We are plagued by earthquakes, lightning, human activity, electronics, laser disturbance, scattered light, and other unknown glitches all the time. It's like the universe says, here's a gravitational wave, and Earth's like, well, cool, here's a truck driving by. And actually, I do have a funny story. Our Livingston Observatory did have a interesting glitch that took some time to investigate, and they checked the security cameras to see that a bird was sitting on one of the detector arms. So yeah, very, very sensitive, and anything else is pretty much noisier. Well, so then Urja, how are you detecting these guys? So we do a method here that I will shortly and quickly explain. So we know from general relativity a little bit about gravitational waves, black holes, and neutron stars. So we take all of that wonderful, elegant math and we turn those into templates. So these are waveforms, in other words, or just examples of what we think a gravitational wave could look like given certain conditions. So we take our detector data that we call strain data, and we compare it to these known mathematical templates that we pre-compute and build. For what I do, we have 2 million templates that we actively look through each segment of data with. And we perform something called match filtering. So match filtering is that comparison process between the template and the live data. And you have this template here sort of comparing between each segment of time and that data that is shown in black. And if there is something interesting present that matches with the template in the data, then we get a peak in this plot that is labeled SNR, which we call signal to noise ratio. That is one of our detection statistics. And if we have that, then we go, I found it. And you know what? In 2015, that is exactly what happened. So on September 14, 2015, while our observatory was in its first observing run, Hanford and Livingston observatories both saw the very first gravitational wave detection from a system of 2 black holes. So we call that binary black holes. Now, each of those black holes were about 36 times the mass of our sun and 29 times the mass of our sun, which is pretty big. It was seen by both the detectors, like I mentioned, so very confident detection. And the final black hole that was formed after the collision or after the merger had a mass of 62 solar masses. So if any one of you is able to do mental math better than me, the total mass should be 65 solar masses, or 65 times the mass of the sun, if you just add these two numbers together. So we're missing 3 solar masses. And what happened to that? If you were thinking or guessing that it was radiated away as gravitational waves, you were absolutely correct. So 3 times the mass of our sun's worth of energy was radiated away as gravitational waves. And the distance from us to that event is 410 megaparsecs, which may not mean a lot to most of you, but if I convert that, that means it's 1.3 billion light years away, which means that we saw something in 2015 that happened about 1 billion years ago before complex life existed on planet Earth. That is mind-blowing, and we see this now all the time. So this work, rightfully and very deservingly, garnered the 2017 Nobel Prize in Physics to Barry Barish, Kip Thorne, as well as Rainer Weiss. We did not stop there. So we had our first observing run here. That is our very first detection. We had 3 detections that first observing run, and now it's been 10 years since LIGO has been operational, and we've had over 218 events so far, many more big booms. And that is not including all of these events that you see here in hollow circles, which are unconfirmed yet, but will soon be released as we're working on our data release. So what was something that was so rare and happened we thought we were lucky that we saw the very first detection. Now, when we are in our observing runs, is almost a daily occurrence for us. Fantastic question. Can we retire? Are we done? Should the government stop funding us? Exactly. Nope. Well, we're kind of selfish. We do want to continue seeing more black holes and neutron stars because I think we can continue to learn interesting stuff about them as we have more detections. We want to see fainter signals. We want to be able to see things further away as well. We want to be able to catch them faster. And I'll bring that back up a little later. Right now, we're able to see them at a rate of a few seconds, like even as soon as like 6 to 30 seconds. But we want to shorten that time even more. And lastly, we want to find new stuff. I mean, black holes, don't get me wrong, are super cool, but we've seen over 200 of those. We want to see something new as well. So we're still on the hunt for something different. And thankfully, LIGO is not alone in this mission. So we have loads of other observatories that are planned or operational that will be spanning the huge frequency range of gravitational wave sources as well as timescales. So LIGO detects things that happen in like milliseconds of times, but you do have certain sources such as the spinning neutron stars that I mentioned earlier that could be years-long gravitational wave signals, which the pulsar timing array is wonderful for. So we are going to be joined by LISA, which will be essentially LIGO in space that will be detecting really massive black holes, much more than we see at LIGO as well. So we have a great plan for all of the gravitational wave sources coming up, but some of that wouldn't be for the next several years. But what's next for LIGO? We are currently right here towards the second half of 2026. As I showed you, we have completed the fourth observing run very recently, which is very exciting, and we are going to publish our data release very soon. We are preparing to start for an intermediate run one, IR1, that is starting around October. That will be a 6-month complementary run to the Vera Rubin Observatory. So if you are aware of Vera Rubin, it is an optical telescope that is incredible. It's doing a decade-long survey, but it has a partnership deal with LIGO where it can devote some percentage of its time to follow up on LIGO events. So we're doing this joint venture to see if we can see anything cool together in the optical spectrum of light. And from there on, we hope to have some more detector upgrades after IR1, and we plan to start our 5th observing run sometime in 2029. But everything you see in the dashed lines here is not confirmed and planned but unsure of. So that's what we're hoping for. Now you may be thinking, Urja, you've been blabbering so much. There's 1,600 members. Why are you important? Why are you here? So to talk a little bit about where I come into this work, I focus on real-time gravitational wave detection with this wonderful group right here called the GST-LOL group. We do live detections of gravitational waves within seconds. So data comes in real, we have our pipeline running constantly, and we detect by black holes and neutron star mergers with gravitational waves in real time. This is very, very valuable because of something called multi-messenger astronomy, which is also another focus of my work. So multi-messenger astronomy essentially means to be able to see the same source in different means. So for me, that would be gravitational waves plus something else. And where I am really interested in is gravitational waves plus optical. So when we have live detections and we're able to see things in near real time, we can inform our astronomy community about it instantly. And we do have a network that goes out. We have a circular that informs astronomers worldwide at different observatories saying, hey, LIGO saw something cool right over here in the sky. And if they have the bandwidth, they're able to point their telescopes instantly to be able to look at it as well. So that helps us see the same astrophysical event in different modes, which provides increased information. We've had one monumental joint multi-messenger detection back in 2017 of two neutron stars merging. And when two neutron stars merge, they go out in an explosion called kilonova. And that is extremely violent and extremely important too. In fact, from that singular one event, we've learned that the gold that most of you are wearing today comes from kilonova explosions and binary neutron stars merging. So now you have an idea a little bit about why this is so important. We have been able to confirm the source of heavy elements in the universe, such as gold. And lastly, I also look at population study for black holes. So events that are not as significant to us, but are still detected, are very interesting because they could be from interesting physics, or they could also be from really further out distances. So what does that really mean? Could that tell us a little bit more about what the universe looked like back then, or what systems were around, or why they formed a certain way? So those are the type of questions that I try to ask in my research. Now we're towards the end of my talk, so I wanted to share with you some useful QR codes. If you are interested in this type of work, that are some of my favorite to share at public talks. So this one here is the live LIGO detector status. You can actually record or see in real time what the sensitivities and operational status of different ground-based gravitational wave observatories are. The second one here is a public web page that we have that records gravitational wave events as they happen. So we also publish our live detections here. It's called GraceDB. You will also find past detections on this, including things like different pipeline analysis and stuff. And one of my favorite features of this website that I particularly use a lot is that you can set up phone alerts, text or call alerts to notify you when something interesting happens. And I use that all the time. So I find that really cool. Lastly, I do have my LinkedIn here if you would like to connect with me or know more about this work. And for being such a wonderful audience, I am paying dog tax. Here's my dog, Hubble, and hence the only Hubble image that matters. And I want to thank Astronomy on Tap Atlanta for giving me the opportunity to speak here. I've had a wonderful time. Please follow their website and Instagram for upcoming events, and also leave them a tip if you feel so. But thank you, and I'm happy to take questions. Sure. Oh, yeah. Okay, sounds good. Yes.
Why was the first one, why did it take so long to detect the first gravitational, and then why after we detected that, it started happening more frequently? Did our technology get better, or did something change?
Yeah, our technology got better. Oh yeah. So the question was, why did it take so long for us to see the first detection, and why has it been that the number of detections we've seen since then have accelerated in rate? So that is purely due to improvement in our instruments. So we do, or over the time, we've included very sophisticated instruments to help us control noise systems and stuff better, or stabilize our equipment a lot more. At the same time, because we've learned a little bit about gravitational wave events so far, our data analysis pipelines are doing much better since they've learned a little bit of what a signal looks like to then detect more of such signals. So it's been a mix of both.
much for this talk. I wanted to touch on one of the things that you did research on with like population studies. I assume you're probably talking about like gravitational wave cosmology and maybe looking at how the distribution of like masses changes as like a function of redshift. I'm curious to know what your process is for like looking or like developing these populations or these models in your research.
Thank you for that question. That is actually a very early project. So we don't have a lot of information on that as of yet. But what we're looking into is sort of exploring some of our detection statistic methods and seeing why they differ or why they're giving us different results and whether there are parameters in there that we need to, specifically things like mass model, um, that we need to do a little bit more deeper search on. But we're at a very early stage in this project. Yeah, but great question. Thank you.
Um, can you play the video again and tell us like what we're hearing?
Oh yeah.
It's a ways back. Sorry.
Yeah, of course. Let's go. Oh. Okay.
Try going back before this slide and come back.
Yeah, I think that's a good plan. So we're actually hearing like the frequency chirp here. So you can convert these gravitational wave signals into noise, and this is commonly done for outreach. It sounds really beautiful. So that is the chirp noise that we're hearing. This is our signal. That is what it sort of looks like in a frequency space. So it's like a flip increase in frequency thing. If you're familiar with music, that's similar.
Hi, a couple slides from now.
Yeah. Back or
forward?
Okay.
Talk about like all the observations you guys have seen so far. That one right there, that's like ultra high signal. Can you tell me more about that?
Yeah, so that's actually one that we did a special paper on. So that's why that's already been published, and it's not, even though it's been at a later time, it's not unreleased data. That was our extremely loud event ever. It is a binary black hole detection, and sorry, but I don't remember the masses of it. But the signal to noise ratio as a comparison was over 80, and we denote anything over 8 as a detection. Yep, so a very high significance.
So if galaxies and black holes and things like that can cause gravitational lensing, why don't they disrupt? You said that these move through space without being interrupted. Like, do we have a double slit experiment going on here where you're causing these waves to split?
Yes, we do. No, you're fine. You're fine.
So, interesting question. We're not necessarily splitting the wave. And in fact, and this commonly happens, since many astrophysical things might happen at the same time, we do have interacting waves, but they pass through each other as well, mostly undisturbed. So when waves themselves interact too, they're not really affected. So I don't know if that answers your question.
If galaxies distort space-time and distort light and all that and waves, why doesn't it seem to be the same?
With what?
In an extremely curved space-time,
Yeah.
does an extremely curved area of space-time affect the propagation of a gravitational wave? That was my reaction.
Yeah, it's an extremely curved space-time. I don't believe so. But I need to think a little bit more about this, but I don't believe so. It shouldn't distort space-time, or it shouldn't distort the propagation of space-time.
our gravitational
Hi, I know you
lensing
can't see me,
prone
but
to
my question. You
Yes.
were mentioning earlier about
different
basically further
rephrasing.
filtering data and changing the LIGO systems so that they are more attuned to sensing gravitational waves. How are y'all stabilizing that? Can you speak a little bit to that in layman's terms? Because I'm a social sciences major, I don't understand anything. So thanks.
So if I repeat the question correctly, it's how are we stabilizing our system? Okay, yeah, there's a lot of complex equipment that goes into doing this. We have extremely sophisticated equipment that helps us stabilize things really well. We have test masses that are kept in our detector arms that are kept very precise locations. And being in vacuum too, that really helps. And we've never gone off vacuum since 1994, I believe. So we've achieved really good stability in that sense. We are disrupted mostly by external effects now, not as much internal effects. Yeah, but it's kind of hard to describe that without showing you a diagram of the instrumentation that's gone in. Um, okay. I would have to pull that up, but yeah, we have a very complex system of different mirrors and stuff that have also gone in, and lenses that help ensure that our system is as stable as possible. Of course.
Hi, thank you so much for the talk. I was wondering, so in here we can see that from LIGO you can tell how far a black hole or a neutron star is. I was wondering how you can tell how far it is, and also if there's a way that you can also tell like the direction of where it's coming from, or is it just the distance? Thank you.
That's gonna be my question.
Yeah, so we can actually tell where in the sky that they're coming from. And that is exactly why we have a detector network. So, what happens is when a gravitational wave comes down to, say, Livingston, if Hanford is also turned on and operational, it will also be seen by Hanford, but with a slight time delay, which is consistent with just light travel time, gravitational wave travel time, etc. So with that, we can sort of create this map to see where in the sky the source comes from. Now, it is still not great, so we can constrain it to tens, hundreds, thousands of square degrees in the night sky, which is still really, really large of an area for another system to follow up on. But when we have numerous systems such as Virgo, Kagra, along with the two LIGO detectors pointing all together, then it is easier to tell where it's coming from. So as an example, if we only have one LIGO detector that's operational, it is very, very, very difficult to tell where it's coming from. We cannot localize the event well at all. So having more than one detector is crucial. Now, similar thing goes for distance. We are able to use the amplitude and the frequency of the wave itself based on general relativity to tell us how far the event is coming from. We do have a range that I would say we're sensitive to based on the masses of the event. And usually for a 1.4 solar mass to 1.4 solar mass event, which is likely a binary neutron star merger, we have our distance ability is around 150 to 170 megaparsecs away. So for that small of a system. Now, obviously our sensitivity or our range of detection increases vastly if you have a heavier object that is merging. But for 1.4 to 1.4, which is what we use as our scale to tell what our range is for detection, as in '04, in the fourth observing run, it was 150 to 170 solar masses.
Let's get a couple more.
Hi, thank you so much for the talk. Earlier you mentioned that you have a catalog of about 200 million different event types that you guys look for. Is there a possibility that there are events that you guys don't know about and aren't looking for yet? And how does the process go for adding those?
Amazing question. And honestly, it is a huge branch of our collaboration effort. We call those unmodeled searches because we don't really know what their gravitational wave is going to look like. We don't really know the physics that's governing the system really well. So it's really hard to formulate those templates. And unfortunately, I think because of that as well, we haven't seen anything with confidence so far. That is an active area of research, and that even includes seeing the same systems as before, neutron stars and black holes, in merging in very interesting ways that are not the classic orbital rotation. So yeah, we don't really have a plan for these waveforms because we don't have great physics to govern them and model them, or if we started doing that, it would take a very long time and computational effort. So we are some data analysis methods are now using AI and machine learning to be able to train on those. But I think we still have a little bit ways to go to be able to see anything of that sort.
I'm going to hijack the last question.
Yes.
So part of the Artemis mission was scoping out areas to build a already funded moon base. So I know that you all at Georgia Tech pull in a lot of funding, only slightly more than Georgia State. Is there any plans from LIGO or Virgo or LISA to build another array to extend the gravitational wave interferometers to include the moon?
Amazing question. Yes, there is. And in fact, Laura Cadenati, who's right there, her graduate student, who is now a professor at Vanderbilt, is leading a project called LILA, which will be the Lunar Interferometer Gravitational Wave Observatory. I think there's definitely some plans for lunar observatories and missions, but we don't know exactly of where they stand, or I don't know exactly where they stand yet. But yeah, it could be pretty interesting to have seismic noise removed.
Nice. Let's give one more round of applause. Urja.
Sorry, I had backup slides.
One more backwards. To the Astronomy on Tap slide.
Oh.
There we go. All right, just some housekeeping. Astronomy on Tap Atlanta is celebrating their 3rd year anniversary this October. So, any and all information that you will need to find out what we are doing and where we are doing it, it's either of those two